In this video, we're going to talk about orbital motion. We've already determined that the gravitational field acting on the occupants of the space station and on the space station itself is not very different than the force acting on us. So how come they don't fall to the Earth? The gravitational field will be pointed towards the center of the Earth and represents the acceleration that the mass would experience at that location, regardless of its mass. In this case, any object would simply fall to the Earth. How could that be avoided? If the object has a tangential velocity perpendicular to its acceleration, it will go in a circle. It will keep falling to the Earth, but never strike the Earth. I'm going to go ahead and place this link on the website in Edmodo and a separate link for you. Here is Newton's own drawing on a thought experiment where a cannon on a very high mountain above the atmosphere shoots a shell with increasing speed, shown by trajectories for the shell of D, E, F, and G, and finally so fast that it never falls to the Earth but goes into orbit. We can calculate the velocity necessary to maintain a stable orbit at a distance r from the center of the planet, which has a mass m. We know that the sum of the forces is equal to ma. Okay. We know that the gravitational force, which is directed inward, is equal to mv squared over r hat, crossing out the unit vectors and the direction. And notice here we also have a separate r. We could cross that out. We can cross this m out, this m out. The negatives cancel out. The r hats cancel out. And we're left with gm over r equals v squared. So what this tells us is that the speed of the satellite has to be equal to the square root of the universal gravitational constant times the mass of the planet divided by the distance between the center of the planet and the center of the satellite. From that, we can calculate the period of the object's orbit. We know that the speed is equal to 2 pi r over t. This is the speed on a circular path divided by the time period. Solving for the time period, it's equal to 2 pi r over v. We also know that v is equal to the square root of gm over r, and we can substitute this in for v here. So now what we need to do is compute g at a distance of 7.3 times 10 to the 8 meters from the center of the spherical object who has a mass of 3 times 10 to the 25 kilograms. Go ahead and pause the video now to solve this problem. Okay, so let's take a look at the solution. We're going to use g is equal to capital G, capital M over r squared. Substituting in the numbers, we end up with 0.38 meters per second squared. Use your previous answer to determine the velocity, both magnitude and direction, for an object orbiting at a distance of 7.3 times 10 to the 8 meters from the center of a spherical object whose mass is 3 times 10 to the 27 kilograms. Go ahead and pause the video now. Okay, so let's take a look at your answer. We know that g is equal to v squared over r. V is equal to the square root of gr. Substituting in the numbers, you end up with 16,556. Now, be careful about the significant digits. Really, they're only giving us 2 sig figs for this if it's a measured number. If we count it as a constant, then our answer should only have 4 significant digits from this answer here. And so that ends up giving us 16.6 or 16.56 kilometers per second. So be careful with the sig figs. In your previous use your previous answer to determine the orbital period for an object orbiting at a distance of 7.3 times 10 to the 8 meters from the center of a spherical object whose mass is 3.0 times 10 to the 27 kilograms. Go ahead and pause the video. Okay, we know that the period is equal to 2 pi r over v. Substituting in those numbers, you end up with 2.7 times 10 to the 5 seconds. Now, one of the things they didn't say in the previous one, let me go back. They were supposed to give the direction. This is just the magnitude, and I just realized there's no direction. The direction should be tangent to the circular path. Okay, so the velocity is always tangent to that orbit. Compute g at a height of 59 Earth radii above the surface of the Earth. Go ahead and pause the video now. Okay, so let's take a look at the solution. G is equal to gm over r squared. Since for a height of 59 Earth radii above, we're going to replace the h with 59 re. That gives us 60 re squared, which gives us 1 over 3600 times g. So taking g of the Earth, which is 9.8 meters per second squared, and dividing by 3600, we end up with 2.72 times 10 to the minus 3 meters per second squared. Use your previous answer to determine the velocity, both magnitude and direction, for an object orbiting at a height of 59 radii, Earth radii above the surface. Go ahead and pause the video now. Okay, so let's take a look at the solution. We know that g is equal to v squared over r. V is equal to the square root of gr. Substituting the numbers in, we end up with a speed of 1018.23. If we go with 2 sig figs, then it should be 1.0 times 10 to the 3 meters per second, or 1.0 kilometers per second. Okay, direction, tangent to the path. Use your previous answer to determine the orbital period of the object orbiting the Earth, 59 Earth radii above the surface. Go ahead and pause the video. Okay, so let's take a look at the answer. You should end up with 2.37 times 10 to the 6 seconds. Okay, here they use the whole number. I would have used 1.0 times 10 to the 3 meters per second, and then I would have had 2 sig figs in my answer. So my answer would have been 2.4 times 10 to the 6 seconds, or 2.3 times 10 to the 6 seconds. 2 satellites orbit 2 different planets with the same radius but different densities. The density of the first planet is rho, and the density of the second planet is 2 rho. What is the orbital speed of the second planet in terms of the orbital speed of the first? Okay, let me fix this right here. Is it A, B, C, or D? Go ahead and pause the video now and see if you can figure this out. Okay, so let's take a look at the answer. The correct answer is A. It is the square root of 2 VI. Remember, when you're talking about densities, you have to go back to the formulas where we have the density. Remember also that density is equal to the mass per unit volume. Okay, you're not changing the volume of either one, but you are changing the density, which means you are changing the mass per unit volume. 2 satellites orbit 2 different planets at the same distance to the center of the planet and with the same density but different radii. The radius of the first planet is r, and the radius of the second planet is 2r. What is the orbital speed of the second satellite in terms of the orbital speed of the first? Again, you're going to go ahead and do a ratio of the two. Go ahead and pause the video now. Okay, so let's take a look at the, see if you have the correct answer. The correct answer should be D. It should be 2 times the square root of 2 times V1. In the next video clip, we'll talk about Kepler's third law of motion.